let's energize this session.
I'm looking forward to it. Thank you.
Thank you.
Excellent. Well, welcome, everyone. Thank you very much for the opportunity to speak. I'm always excited to talk about fusion. I've lived in Boston for 10 years and actually never been to this venue, so it was a great opportunity to come and see this. It's a very cool place. Yeah, so I'll be talking about fusion, fusion energy, both a bit generally and also the specific path that Commonwealth Fusion Systems is taking to get there. So I will jump in. Great, yeah, CFS and our path to commercial fusion energy. So I think the motivation already came out a little bit. The world needs energy, a lot of it. There's a bunch of projections on this graph that I won't go through, but basically regardless of who you talk to, we need a lot more energy. We need a lot more clean energy. We need a lot more firm energy. I believe there were some sessions this morning looking at AI, specifically Google DeepMind, who we have a partnership with, and that's another addition to the more and more energy needs of the world. And we think at CFS, and more generally people working on fusion, that innovation is a key way to progress energy forward toward clean energy. We need to deploy what we have now, but we also need to work on new technologies. I'll talk a bit in a second around what is fusion, but a little bit why are we interested. It's clean, so the only emission is helium, which is not a greenhouse gas. It's not toxic. You can suck it up and make your voice sound funny. It's firm. So it's on when you need it. It's safe, so there's no harmful byproducts, and there's no risk of a meltdown type event. It's scalable, so this is something that you can build. It's a product that creates energy, and it's secure in that you don't need to import large quantities of oil or gas or something. It's a product that you build and you send somewhere and operates and make energy. So with that as context of why would we be interested in fusion, I'll talk a little bit now about so what is fusion? Very basic. I like cartoons. Stuff is made of atoms. I'm going to draw a lot of red dots and blue dots, protons and neutrons. So just laying that out there. That's not the right number of electrons for gold, but I got bored of drawing electrons. Before I talk about fusion, I'll start with fission. So I'll quote nuclear power today. I think the closest nuclear power plant to here is Seabrook in New Hampshire. Is splitting big atoms like uranium. It releases a bunch of energy, and you can continue that chain reaction. Fusion is the opposite. So you're combining smaller atoms into large atoms, which is what happens in the sun. So specifically, we're working on deuterium-tritium fusion. There's a variety of different fuels you can use. This is the easiest. I'll get to what that means in a second. But two isotopes of hydrogen, one with one neutron and one with two neutrons. If you smash them together hard enough, they will fuse into helium-4 and a free neutron, both of which are moving quickly, so have a bunch of energy. What does smash them together hard enough mean in practice? In practice, that means heating them up to more than 100 million Kelvin. So at some point, it's a number that's so large it almost loses its meaning. But it's a very, very, very hot temperature. And unsurprisingly, that is the temperature of stars. So in order to do fusion, which is what happens in the stars, you need to get your fuel basically to the temperature of a star. I won't talk too much about it, but basically how do we do this? If you're making something that hot, what does it even look like? It will be what we call a plasma. So I'm not going to dig too deep into this, but basically if you have a solid, a bunch of atoms, heat it up, you get a liquid, they move around a little bit. Heat it up more, you get a gas, they move around some more. If you heat that up even more, you actually separate the ions, the nuclei, from the electrons. And they move around in a soup, a mix of independent electrons and independent ions. We call this a plasma. And depending on which type of atom you have, it happens at something like 10,000 degrees. So if you get something about 10,000 degrees, often you'll start to ionize it or make a plasma out of it. That sounds esoteric, maybe. But there's actually quite a lot of plasma around us. So as I said, all stars are plasma. The northern lights, the aurora borealis, that's a plasma. I have my nice Boston picture up there. Lightning is a plasma. And actually, neon signs. So there's a little bit of neon in there that you ionize, turn into a plasma. You might say, wait a second, I'm pretty sure that neon sign is not 10,000 degrees. That's a fair question. It turns out that there's so few particles in a neon sign, it's almost a vacuum, that even though each individual particle has a lot of energy, something like 10,000 degrees worth of energy, there's so few particles that the actual sign doesn't get very hot. So plasmas are sometimes easier to handle than you might think if you have a very, very low density. So all that is to say, we think fusion is a very, very disruptive source of energy. In order to do fusion, you need to get your fuel really, really hot. And anything hot enough to fuse will be a plasma. Just running through that here. So how do we plan on doing that? You have to think carefully to get something ready to be heated up to 100 million degrees. We use a type of machine called a tokamak, which was brought up earlier. I won't go through too much what this plot is, but basically it's a summary of there's a lot of kinds of fusion machines in the world. There's donut things and circular things and spheres and cylinder things. People built a lot of these. And this very busy plot, I will apologize, is basically on the horizontal axis, it's temperature, how hot is it? A KeV is a weird physics unit, which is roughly 10 million degrees. And then this plot here is the density, so how much fuel do you have, what's the density, and then the confinement time, which you can think of like insulation. How well insulated is your fuel that you're getting hot? So in order to do fusion, you want to be here on the top right. That means it needs to be hot enough, and it needs to be dense enough and well enough confined, or good enough insulation. And so we've chosen a tokamak. There's more than 100 of these built around the world, so it's a relatively well understood technology. And the goal with all of these is to get it up into the right toward this region of net energy production in the top right. People built tokamaks. The challenge so far has been making a tokamak that works well enough, that insulates your fuel well enough, that the energy you get out from fusion is more than the energy you have to put in to keep it hot. And so we call that ratio Q, the gain, the fusion gain. Where it's fusion power divided by input heating power. And so the goal in fusion for a very long time has been to get Q greater than 1. In 2022, Lawrence Livermore National Lab did this with a laser-based system where you put a little pellet of fuel, compress it with a bunch of lasers, that makes fusion. We plan on doing this with this magnetic system called a tokamak. So what is a tokamak? It's a bunch of magnets. This is obviously a cartoon, but basically you have the plasma, which is my little orange donut here. You have these big, we call them toroidal field coils. Torus is just the math word for donut-shaped. So these are magnetic field coils that make a magnetic field in a donut shape. And then you have other coils we call the central solenoid, and these poloidal field coils, these big ones, to kind of hold your plasma in the right spot. So these keep your fuel in the right spot. They keep it insulated. And that way, when you put the heat in, it doesn't leak out too fast. So at its core, a tokamak is a bunch of magnets that you kind of levitate a plasma in the middle of. I haven't shown here a vacuum chamber. You need to get all the rest of the air out before you do that. But magnets are the key technology of a tokamak. People built a lot of these. I show this one specifically. This is the inside of a tokamak. These little squares here are tiles. They're heat armor on the inside of the machine. I show this one specifically because this is the one at MIT where I did part of my PhD thesis work. Unfortunately, it's taken apart now. Otherwise, I'd say you should go visit it. But there's a bunch of other tokamaks around the world. And so you can see these are highly engineered scientific machines that get you to the conditions where you can create a star inside the Earth. And so this one has no plasma in it, but basically the plasma would kind of circle around that inner ring, or the inner column in the middle. So that column being the central solenoid. Cool. So that's a little bit about what is fusion? Why do you need a plasma to do fusion? What is the specific type of fusion machine we build? It's called a tokamak. So now I'll talk a little bit about our company, Commonwealth Fusion Systems, and where do we think we're going next? So people have worked on fusion for 70 years, since the 1950s. How do we think that we go from really, really great scientific research to a commercial product that is on the grid producing electricity? So background on us, we were founded in 2018, spun out of MIT, where we've raised nearly $3 billion in venture capital, wide range of investors. We are over 1,000 people now. We started in Cambridge, not too far from here. We've gotten too big for our office several times, and we're now based about 45 minutes west of Boston in a town called Devens. So that's a bit about us. What is our path? So our path to a power plant is use proven physics. So there's a lot of other types of fusion machines out there. We've chosen the tokamak because it's the most well-established scientific basis of how does it work. And this, again, is a CAD model of the CMOD tokamak at MIT. Our innovation is new magnet technology. So tokamaks at their core are a bunch of magnets. Unsurprisingly, if you can build a better magnet, we think you can build a better tokamak. We've done that, so I'll talk about that. We then are building this SPARC machine. This is a demonstration. It should produce more energy out than in, so it produces Q greater than 1. It proves the magnet technology in an integrated environment with the rest of the tokamak pieces. And it shows that we as a company can build stuff. And then eventually we move to ARC. That is our commercial demonstration, or not demonstration, our commercial power plant. So that'll be a fully functioning fusion power plant. The first one will be in Virginia. We've announced a site, and we have 2 customers signed up. So Google and the Italian oil and gas company Eni are 2 of the customers via power purchase agreements. So a bit about this path. OK, where are we going on here? A bit about the physics. I won't describe all the physics. I will say that we try to be very open about this. We understand that fusion can seem esoteric. It also gets a bad rap as oh, it's never going to happen. It's always in the future. So at least on the physics side, we publish very regularly and very openly in academic journals to basically help build the credibility of the field and the credibility of our specific approach to fusion. So I won't talk about the specific physics. All of these are open access. If you really want to dig in, you're welcome to read hundreds of pages of fusion articles. But these say that the summary of these, if you can build this machine, it should do net energy, described in excruciating detail. But how do we build this machine? So older tokamaks are all based on copper magnets or low-temperature superconducting magnets, so niobium tin or niobium titanium. These materials are great. This is what we make MRI machines out of. The challenge is they're limited in their maximum magnetic field. So you can only go up realistically in a tokamak geometry 5, maybe 6 Tesla where the plasma is, on the plasma. But like I said, in fusion, a lot of stuff gets better with magnetic field. And recently, there's a fundamentally new technology called high-temperature superconductors, HTS. Specifically, there's a version called REBCO, rare earth barium copper oxide. It's a ceramic. It was discovered in the 1980s, won a Nobel Prize by some scientists in Switzerland working for IBM at the time. But up until recently, you could only make very small quantities of it in a lab somewhere. But over the last 10 years, it is now available in industrial scale. And our innovation has been to turn that raw material, it looks like a ribbon, into an industrial scale magnet that you can use for fusion. So this D-shaped thing here is our model coil we built in collaboration with MIT about 4 years ago. The peak field on that coil is about 20 Tesla. And so for reference, a typical MRI machine is about 1.5 Tesla. Some go a little bit higher than that for research machines, but a normal hospital MRI is about 1.5 Tesla. That's the largest magnet most people would interact with in their a normal life. Whereas this is more than 20 Tesla on coils. So it's very high. That would translate to something like 12 Tesla on the plasma, so more than double what the previous generation of magnet technology could do. And in fusion, a lot of stuff goes magnetic field squared or cubed or to the 4th power. So by doubling the magnetic field, you get a real win in a bunch of stuff. I won't talk too much about this, but we've developed and tested other magnet technology as well. We also actually now deliver magnets, very high field magnets, as a kind of a side business in addition to doing fusion to other customers. SPARC. So this is the one we're building now. This is an overhead view. A little bit hard to get a sense of scale, but these are trucks and stuff. It's big. This is the facility. It's kind of power plant sized, which is perhaps unsurprising given it's close to being a power plant. It is what many physicists would describe a very boring tokamak, in that the physics inside of the tokamak is not very interesting. That is intentional. People don't want exciting power plants. They want really boring power plants that sit there and make electricity. It's now under construction, so I'll show some pictures here in a second. I think the 2 things I'll highlight. It has 2 main goals. One I've summarized is do Q greater than 1. That's perhaps overly simplistic, but we need to prove that out. And 2 is learn stuff for our commercial power plant. So again, overly simplistic, but the reason we're building this is to prove we can do it, but also to learn things as we go to our commercial unit. So yeah, big facility. This is our headquarters building here. our manufacturing facility is about 100,000 square feet to manufacture the magnets, and then the SPARC plant there in the background. This is an industrial facility, so we're now in the midst of installing a bunch of like very large industrial systems. This is a 8 Kelvin cryo plant that we're installing. We're now commissioning it. I'm in the process of commissioning it. We are now started assembling the machine itself as well. So this is the room we call the Tokamak hall. This is where the Tokamak itself will be. This is the first component of the actual Tokamak, the base of the cryostat that we're installing. The machine in total is about 1,000 metric tons. So it's pretty heavy. And this is kind of the first piece, the foundation that the whole thing goes on top of. We actually had really nice pictures yesterday that we released of the newest component, the vacuum vessel that came in, which I didn't have time to put in my slides. But if you go to our website, there's really cool pictures of like the next set of components coming into the hall. This is actually an earlier version of the vacuum vessel. This is the piece that you put the plasma goes inside that you use. You pump out all the air so you can make the fusion. Have low enough or have a pure enough hydrogen plasma that you can do fusion. Big industrial pieces of metal. We build all of our own magnets. So as I said earlier, our key innovation is the magnet technology. We have our entire fairly vertically integrated magnet manufacturing facility, and this is our kind of key piece. This factory was empty 3 years ago, and now we are nearly done building all of the magnets for this first machine. So we went from like an empty room to basically being done with our first full run of production in about 3 years. Some other pictures of a detail of one of the magnets. This one's not kind of in process being manufactured and tested. So we test all of the magnets at their operating parameters before we put them into the actual tokamak. So that's SPARC. It is a demonstration machine. It proves out fusion as a eventual process. It proves out this magnet technology in an integrated system, and it proves us as a company that we can actually do stuff. We're still a startup, but it's not a product. That's not a power plant. And the goal in all this, as I said at the very beginning, is we need to go build a power plant. The goal of fusion in the long term is clean energy on the grid, and so that'll be our ARC facility. And so, SPARC under construction now should be operating in 2027 approximately. ARC we plan to have operating in the early 2030s. That's intentionally a little bit vague. We don't want to promise a specific date until we have a much better sense of the schedule, which we are working on. But early 2030s is the current kind of operational target for ARC. It's bigger. So you can see here people for scale. So it's a bigger machine. Linear size, it's roughly twice as big as SPARC, but a lot of stuff scales like volume, so it's 7 or 8 times as heavy. And what is it? It is a 400 megawatt net electric power plant. So put that into context, that's like a very small nuclear fission power plant, like a medium-sized natural gas, combined cycle natural gas turbine facility, somewhere in that range. We chose that number not because we really like 400, but because basically if you go out and talk to the market, if you go out and talk to utilities, they're really interested in this kind of medium-sized facility where you can stamp out a bunch of them rather than having to get a giant gigawatt thing from the beginning. So this allows you to be a bit more flexible. It works well in the existing grid that is very heavily, at least in the US, built around combined cycle natural gas plants, can plug into the same interconnects in many ways. And it works well for the customer perspective. Or a very small coal plant. The other one we're looking at is in the US, there's a lot of coal plants that are shutting down. And so this may be able to plug into existing coal infrastructure with the grid interconnect and things like that. We've announced our site. Like I said, it's just outside of Richmond, Virginia. We announced that a little under a year ago. And we announced customers for it as well. So Google and Eni will have signed power purchase agreements to buy electricity from ARC. And I think the last thing I'll say here is that fusion, at least today, is primarily a research pursuit. It's people doing research to get this first-of-a-kind to market. I think we, as a company, have thought a lot about, in order for fusion to really matter at a global scale, on the scale of climate change, you need to build thousands of these power plants. You cannot build one. You cannot build 10. So everything we do has to have the mindset of eventually this needs to scale to thousands of power plants. Otherwise, fusion's kind of a cool little niche thing, but it's not a solution at the scale of the problem of climate change. So This is our path. We're building on this known physics of tokamaks, these fusion machines people have built. Our key new innovation is like a fundamentally new magnet technology that we've now demonstrated. We're going to this SPARC machine, which we're building now to show the whole thing all together. And then our key next step after that, which we are in the early stages of, is the ARC fusion power plant, the first of which will be in Virginia. That's what I have. So I'm happy to take questions, and thank you very much for your attention.
Thank you very much, Alex. I'd say it's an electrifying topic.
I hope so.
Yes, we have time for questions. Maybe I'll start with one, if you allow me. This new magnet technology, how did you invent it? Was it purely on physics studies, or did you use AI as well? How did you come to that new level?
Great question. Yeah, so it was a lot of engineering study, a lot of physics study, and a lot of like R&D trial and error. Of like take this conductor and do stuff with it until it works as a magnet.
So no AI there?
Not yet. I mean, that new magnet technology was in like 2016, 17. So like
a little bit before.
A little bit before. The transformer hadn't yet been invented or discovered, however you say it. But I think, as was mentioned earlier, like we do now incorporate AI into our manufacturing processes for like automated flaw detections. We are working on incorporating it into our control system for the plant. So it's really getting very actively involved now. But 10 years ago when we were in the magnet, it was like a little bit maybe premature.
And because you mentioned, of course, DeepMind, and then you said that Google was going to be a customer, we all have this big elephant in the room, which is the increasing demand in electricity for AI and AI factories. So without, of course, revealing any plans, are you prioritizing all the AI factories to be the energy supplier for them, or?
Not necessarily. I mean, we have some of them. I mean, Google has signed up. NE's not an AI company yet. Maybe they will be. I don't know. But we're open to selling to multiple customers. I think generically, AI and fusion are complementary in that the most recent AI models can help control, can help design, can help improve fusion, and hopefully fusion can help power the new AI energy needs.
Any questions from the room? Over here.
Very exciting presentation. As a physicist, I love your work. I hope to succeed.
Thank you.
But as a businessman, I cannot resist. So how is the cost of your energy comparing to the cost of coal, gas, and fission?
Another elephant in the room.
No, it's a good question. So as I said to begin with, like one of our core principles as like a company is that for fusion to work, it needs to work in a market. So it can't be too expensive, otherwise like no one's going to buy it, and like that's not a good solution. Our current projections put fusion at like cost competitive with firmed renewables, so renewables that have enough battery storage to like be firm. Probably like not quite exactly at parity with natural gas in the United States because it's very cheap, but in that range, and significantly cheaper than like new fission, which in the US currently is very expensive. So we're not going to promise that it'll be the cheapest form of energy ever, but we think it's cost competitive with existing sources that have similar attributes.
Very clear. Other questions? I guess that was clear, plasma clear.
Perfect.
Thank you very much. Let's thank Alex again for this amazing presentation. Makes me want to work for you.